Welcome back to our third and final segment. We're still looking into the quantitative aspects of chemical change, but now we shall focus our attention on the empirical formula. Right, so now we understand the chemical formula. We also understand percentage composition in terms of elements making up, a compound, and this is has to do with the mole ratio. But now we want to focus our attention on the empirical formula, right? Okay, what's empirical formula all about? So the empirical formula of a compound, it's always about a compound. It means it should be more two or more different types of elements that are chemically joined. So the empirical formula of a compound actually shows the simplest mole ratio. So those are the key terms. It's the simplest mole ratio in which elements of a compound have bonded. So our emphasis is on the mole ratio in its simplest form. Okay, so these substances' actual molecular formula could be multiples of each empirical formula. So if we get the simplest whole mole ratio of each element that is in a compound, if you double it or treble it, it could in some cases give us the actual molecular formula of the substance. So the empirical formula of a compound can be calculated from its percentage composition. Right, so percentage composition, something that we know, we're expressing the mass of each element as a percentage of the total mass of the compound, right? And then what are the steps that we have to go through in terms of determining the molecular formula? Okay, first of all, express the percentages of each element, in terms of a 100-gram sample. So for argument's sake, if we say a substance is 35%, it means for every 100 gram sample, that element is a mass or contributes a mass of 35 grams. Okay, so we convert the mass of each element to the number of moles, okay, because it's always about the moles. Because remember, the empirical formula shows the simplest whole number ratio of moles of each element. So at the end of the day, we must determine the moles, right? Okay, then we can simplify because this is the simplest whole number. And when we talk about whole number, we're talking about integers. I think you recall that very well. Here is a typical example with a compound that is made of 36.5% sodium, okay? Right? We also have 25.4% of sulfur and then 38.1% of oxygen. Then we want to determine the empirical formula of this compound. Now, before we even do all the complex calculations, let's think about this way. Are we able to guess the chemical formula that could be between, because it contains sodium, sulfur and oxygen in that order? We shall maintain that order. So we've got sodium sulfide and sodium sulfate. Okay, now if you look at the percentage by mass, let's say for argument's sake, compare sodium to oxygen. In the sulfate, it's 2:4 for sodium to oxygen ratio, while in the sulfide is 2:3. So this is a sulfide, okay? This is a sulfide, and then this is a sulfate of sodium, okay? Okay, that's the difference. So the difference lies in the complex polyatomic ion there. Okay, so you just check that the oxygen is 38.1 while sodium is 36. So these two are much more comparable. Why in the sulfate is almost double. So let's think about that in terms of predictions, okay? Now, if we are to do the actual calculations, so of this sodium, let's simplify the mole ratio of sodium. So 36.5% is sodium. Let's express this as a percentage, right? Now let's determine the mole ratio of each of these substances. So if 36.5% is the percentage composition of sodium in the compound, it means for every 100-gram sample, 36.5 grams is actually sodium. So we are simply saying that 36.5 grams, which is for 100-gram sample, divided by the molar mass of sodium, which is 23 grams per mole, okay? While for sulfur, it's going to be 25.4 grams, okay, per every 100-gram sample, divided by the mass of sulfur, which is 32 grams for every mole, right? And then for oxygen, we've got 38.1 grams for every 100 gram sample divided by the molar mass of oxygen, which is 16 grams per mole, right? So what we get in each of these calculations is actually the mole in terms of each element, okay? So if we go to our calculator, we will get 36.5 divided by 23, okay? That gives us, okay, 36.5, just to 36.5, okay, divided by 23, okay? What do we get? This gives us, as a decimal fraction, 1.59, okay? Okay, 1.59 mole, okay, right? And then if we go to the second one, what do we get? 25.4, okay, divided by 32, okay? What do we get as a decimal fraction, 2 decimal places? Okay, this is 0.79, okay, right. Just to go back to that, 0.79 mole, right? And then the last one for oxygen, what do we have? We have 38.1, okay? We divide that by the molar mass of oxygen, which is 16 grams per mole. That expressed as a decimal fraction is 2.38, right? So that is 2.38 moles, right? Now, if we are to express the ratio in terms of sodium is to sulfur is to oxygen, in the simply, and we want to simplify the mole ratio, we have got 1.59, right, is to 0.79 is to 2.38, okay? So now we want to simplify this because we want to get the empirical formula. So we'll definitely divide, let's say, by 0.79 throughout, okay? All right, 0.79 divided by 0.79, right? Okay, so if we go back to our calculator, we will have, obviously, this will give us a 1, but we'll do the 1.59, okay? 1.59 divided by 0.79, okay? This gives us a number, 2, okay? We'll get a 2 there, right? So this is a 2 is to 1, okay? Is 2, let's simplify the other end, which is 2.38, okay? 2.38 divided by 0.79. This gives us a what? We'll go back to, this gives us a 3, all right? So this gives us a 3. So the ratio of sodium is to sulfur is to oxygen, in the simplest whole number ratio is going to be sodium 2, and then 1 atom of sulfur, 1 mole of sulfur, and then 3 moles of oxygen. So this is our empirical formula. So the substance in this case is going to be our sodium sulfate. Now, what's the long and short of this? These are the different steps that we carried out in terms of determining the empirical formula. So at the end of the day, we want to appreciate that the chemical formula of an element or a compound, it gives us the ratio of moles. It's always about the moles of each element that is present in a substance, which in most cases is actually a compound. And then the percentage composition actually gives us the percentage ratio of the masses of each substance. And then the last that we did, the percentage composition is a measure of the moles of each element present in a 100-gram sample, because we want to express this as a percentage, right? So those are the main ideas. And then the empirical formula, okay, it gives us the simplest whole number ratio of moles. It's always about the moles, okay, of each element that is present. Now, and then the molecular formula is the actual formula of the substance is a chemical formula that gives us the exact, which is the actual whole number ratio that makes up a molecule. So these are the different types of formulae in terms of the percentage composition. We also looked at the masses. So there's a whole range, of ideas that we managed to discuss in terms of percentage composition, molecular formula, as well as empirical formula. I certainly hope that makes a lot of sense when it all comes together. So that's the time that we have for today in terms of, the quantitative aspects of chemical change. For now, it's cheers and bye-bye for now.